Jai Hind everyone. I am Shruti Jain, Assistant Professor, MC Department, Ajay Kumar Garg Engineering College. The topic that I am going to discuss today is disk scheduling in operating system, and the subject code is BMC203. Let's understand what the storage systems are. As we know that a storage device is any device which is used in a computer to store the information. It retains this information whenever the computer is switched off. So, it basically stores that information into its space. So, the type of the storage device that is being used, it varies based on the type of data and the rate at which it is created and used. So, the examples of storage devices are basically the hard disk, CD-ROM, magnetic tape, removable media, etc. So, whenever we are talking about any of the disk, it has its own structure. It is basically a one-dimensional array of logical blocks, where the logical block is the smallest unit of transfer. So, when we are talking about the one-dimensional array, it is mapped into the sectors of the disk sequentially. Sector 0 is the first sector of first track on the outermost cylinder. This mapping proceeds in the order through that track, then the rest of the tracks in that cylinder, and then through the rest of the cylinders from the outermost to the innermost. Then comes the scheduling of the disk, the main topic that we have. If we are talking about the usage of the hardware, the OS is basically responsible for using the hardware efficiently. For the disk drives, this means having the fast access time and disk bandwidth. The access time has basically two major components. The first one is a seek time and the other one is a rotational latency. So, seek time is basically the time from the disk arm to move the head to the cylinder containing the desired sector. So, it is the disk arm is moving its head to the cylinder and it is moving to the desired sector where it basically wants to access the data from. Rotational latency, that is the additional time that is waited for the disk to rotate the desired sector to the disk head. So, the time between the rotation of the disk in order to get to the desired location, that is rotational latency. So, what we try to do is, we try to minimize the seek time, and that seek time is basically considered equivalent to the seek distance, because the time that is being taken to rotate the disk, that is a waiting time, that waiting time basically becomes the seek time and hence the seek distance. So, if the desired disk drive and the controller are available, then the request can be serviced immediately. If the drive or the controller is busy, any new request for the service will be placed on the queue of the pending request for that particular drive. When there is a multi-programming system with multiple processes, the disk queue may often have several pending requests that are there for different processes. So, when one request gets completed, the operating system chooses which pending request to service next based on the priority scheduling, or maybe the first come first serve or the shortest remaining time. So, it will choose the process and on the basis of it, it will execute that pending request. So, several algorithms exist to schedule the services of the disk IO request. We'll do those algorithms one by one, and we'll take the request queue from 0 to 199, and this is the reference string where the head pointer is at 53. So, the first one that we have is first come first serve. This is the queue which is being required by any of the process. The current position of the head is at 53. So, what it will do in the first come first serve, it will take the queue as it is and will start executing it, or will start performing the action. So, from 53, it will first go to 98. So, from 53, it goes to 98, 98 to 183, 98 to 183, then suddenly to 37, then from 37 to 122 it will go, From 122 it is 14. From 14 to 124, 124 to 65 and finally to 67. Now if we look onto the figure over here, the swing from 122 to 14, this swing from 98 to this swing from 122 to 14, and then again 14 to 144, that is approximately moving to the same side, illustrates the problem with this schedule. So in this case, what is happening? It is moving as and when the requirement come in the queue. So in that case, there is a very long time waiting for the disk to move. The rotational latency is very high over here. And if we see, if the request for the cylinders 37 and 14 could be serviced together, and then 122 and 124 would be serviced together, in that case, the total head movement could have been decreased substantially, and hence the performance could also be improved. So if we try to find out the seek distance, total seek distance, in this case would be, it will start from the head, from source to destination. So the first one becomes, we'll take the absolute value of it because the distance is always positive. It started with 53 and ended up at 98. So it would be the absolute value of 53 minus 98 plus the next distance is from 98 to 183. So that would be 98 minus 183 plus the next one would be 183 to 37. So that would be 183 minus 37 plus from 37 it moved to 122. So 37 minus 122. We need to take care that the distance calculation will be always from source, from where it started to where it ended up, source to destination. Then from 122 to 14, it would go from 122 to 14. This is 122 to 14. 14 to 124. So 14 to 124 plus from 124 to 65. So it would be 124 to 65. This is 65 plus 65 to 67. 65 to 67. So this is the total seek distance that is given to us, that we'll calculate. So when we solve the whole of this, we'll get the total seek distance when we are working with the first come first serve schedule. The next scheduling that we have is shortest seek time first. In this case, like in the first come first serve, what we were doing, we were traversing the queue as and when any of the requirement comes up. This won't be the case in the shortest seek time first. Here we believe that the requirement for this schedule, for the traversing of the pointers is already given to us. The traversal will work on the minimum seek time that is there from the current head position. Now, since the seek time increases with the number of cylinders traversed by head, the shortest seek time first chooses the pending request closest to the current head position instead of moving from one place to another again and again. It gives a substantial improvement in performance. It is essentially a form of a shortest job first scheduling when we are working with CPU scheduling, and is like and it basically leads, it might lead to the starvation of some of the requests. So here we remember that the request may arrive at any time. Suppose that when two requests in the queue for cylinder 14 and 186 have come up, and while serving the request for 14, a new request near 14 arrives. So in that case, what will happen? The new request will be serviced next and 186 has to wait. While that 186 is waiting, again a new request nearer to 14 came up. So in that case, what will happen? There would be the acceptance of request near 14 would be taken up, while 186 will keep on waiting indefinitely. So this waiting of 186 indefinitely would again become a serious issue, because that pending request keeps the queue growing longer and longer. So if we look at to this SSTF, we have the queue given to us, the same queue is there, but now we'll do this execution with the SSTF format. So the head pointer over here is 53. Out of this queue, we'll look for a value which is nearest to 53. So when we look at the value nearest to 53, it would be 65. So the next value to be traversed is 65. Near to 65 is 67. So 67 will be traversed first. Now if we look here, we have two values that could be traversed. The first one is 37 and the other one is 98. If we find out the difference between 67 and 37, if we find out the difference between 67 and 37, that comes out to be 30. And if we try to find out the difference between 98 and 67, it comes out to be 31. So the nearest value that is to 67 is 37. So it will move to 37 over here. Once it moves to 37, the nearest value to 37 is 14. So 14 will be traversed here. It will again check the nearest value to 14. The nearest value to 14 now is towards the right and is basically this 98. So the 14 will, the next value to be traversed is 98. From 98 it will go to 122, 122 to 124, and finally it will traverse this 183. Now when we'll find out the total seek distance in this case, the total seek distance would be, it started with 53, landed up to 65. So 53 minus 65, it started with 65, landed up to 67, so still 67. From 67 it went to 37. So 67 to 37, 37 to 14, from 14 it landed to 98, so 14 minus 98 plus, from 98 it landed to 122, so that is 98 minus 122 plus 122 to 144. So 122 minus 124. From 124 it landed to 183. So from 124 it landed to 183. Absolute value is again taken up because we believe that the distance is always positive in nature. So we'll calculate all of this and we'll find out the total seek distance. When we'll find out the total seek distance, we'll see that the total seek distance from this FCFS is greater than the total seek distance of FCFS is greater than the total seek distance of SSTF. So this shows that the head movement is more in the first come first served scheduling than the movement in the SSTF, that is shortest seek time first scheduling. The next scheduling that we have is scan scheduling. Now what happens in the scan scheduling? The disk arm starts at one end of the disk, move towards the other end, that could be either towards the left or towards the right, servicing the request as it reaches to each cylinder until it gets to the other end of the disk. At the end, the direction of the head movement is reversed. It again starts servicing and the head continuously scans back and forth across the disk. So it is like in a zigzag manner where the disk movement starts from the head position. It either moves towards the left or towards the right. It serves all the requests that comes on its way, changes its direction, and then move to the next side. So the scan algorithm is sometimes called the elevator algorithm, since the disk arm behaves just like an elevator in a building, first servicing all the requests going up and then reversing to the service request the other way. So if we look over here, it is a kind of a elevator situation here. So let's see how it works. Here again, the queue is the same that was given to us. The head start is at 53. So it will start with 53 and it moves towards the left first, servicing all the requests towards the left. So the first request to 53 is 37. So it will start from 53 and moves to 37. The next request to 37 is 14. So it will move to 14 from 37. The next request is towards the right hand side, that is 65. So what it will do, it will move to the last position over here, the last cylinder, that is the initial cylinder from 0 to 199. It will move to the initial value 0 and then start moving towards the right hand side. So moving towards the right is traversing 65. So it traversed 65. Then from 65, it traversed to 67. So it will be 67. From 67, it will traverse to 98. So it will traverse 98. 98 to 122. So this is 122. From 122 to 124 will be traversed. And finally, the value 183 will be traversed over here. So what is happening? It is first traversing towards the left, traversing all the values towards the left, the lower end side. And as it moves towards the higher end side, it looks like a elevator like this. So when we'll find out the total seek time, the method is same. We'll start with 53 minus, it traversed 37 first, serviced 37. Then from 37, it moved to 14. Then from 14, it moved to 0. From 0, it moved to 65. From 65, it moved to 67. From 67, it moved to 98. From 98, it moved to 122. From 122, it moved to 124 and finally to 183. This is how we will calculate the total seek time for the scan scheduling. The next one that we have is C-scan scheduling. Now, C-scan scheduling is kind of the scan scheduling, but in C-scan, the C-scan moves ahead from one end of the disk to the other, servicing requests along the way. When the head reaches the other hand, it immediately returns to the beginning of the disk without servicing any of the requests on the return trip. That means it will move to one direction in this way. As soon as it reaches the end point, it will move to the first point, to the beginning point without any traversing over here. While in scan, we have seen that the traversal was happening while it was onto the scan side. In this way, it moved to the beginning and then started traversing towards the right. But in C-scan, it will not traverse when it returns to the beginning of the disk or the cylinder. It returns to the beginning and then again start traversing it. So here the head is at 53. It started towards the right. It will traverse 65, then 67. After 67, it will traverse 98. then 122, 124, 183. After 183, it will reach to the last point, that is 199. It will come back to the beginning, then will traverse 14 and 37. Finding out the total seek time, would be 53 minus 65 plus 65 minus 67 plus 67 minus 98, 98 minus 122, 122 to 124, 124 to 183, 183 to 199. Now, when it is moving from 199 to 0, so we'll have 199 to 0 because it is again traversing. Then from 0 to 14 and 14 to 37. So, this is how it would be finding out the total seek time in C-scan. So, we have seen multiple scheduling algorithms for disk. The disk scheduling algorithm, the choice of the disk scheduling algorithm basically depends upon how the request has been given in the queue that is needed over here. And our main aim is to reduce the total seek distance. So, that is all for today. Thank you.